Once upon a time, in a land far, far away. Right, story time's over. Let's dive right into the real stuff. However, there is still some magic and beauty that lies within shading. Rendering in OpenGL has drastically transformed and evolved over the years. As new technology emerges, the API constantly needs to keep up with latest demands and work in a more efficient manner. The newer programmable pipeline introduced shaders, which allows programmers more control over the graphics pipeline. This pipeline is essentially a sequence of steps executed to transform a 3D model in its raw form into a 2D object displayed on the player's game screen. Previously, during the fixed function era, all the programmer had was a set of predefined routines that manipulated the graphics pipeline automatically. Okay, so before we delve into any kind of programming, let's first get a little bit of an understanding of how shaders work or how this programmable pipeline actually works. Okay, so I'm going to use a very basic little demonstration here. So what I'm trying to do is get this 3D model, this 3D cube. Let's say you've just made it in Maya or Blender or ZBrush, whatever. Spent hours making it, and you want to project or display this cube in its 3D form on your 2D screen. So this is going to go through four main processes. So one is going to be vertex processing. Okay, it's then going to go through rasterization. Okay, then we're going to go through fragment processing. Okay, and then we're going to have a few frame buffer operations happening, and after that we then have it on our screen. Okay, so basically vertex processing is going to take, if you imagine each corner of the cube being consisting of some kind of vertex, okay, and the more complex the mesh, the more triangles, the more vertices. Each of these vertices will be passed into the vertex shader and processed, okay? So we need to know where it is in the world, how the camera is viewing it, what projection you're in, 2D or 3D, that kind of stuff, okay? It's then passed further down the pipeline to OpenGL, which then goes through a process of rasterization, okay? This is creating line by line pixels, okay? So we're creating the fragments, all right? And these fragments are then passed into the fragment shader, and then fragment processing happens where every fragment is taken and dealt with, okay? And then lastly, frame buffer operations, where we actually convert that, we take those fragments or pixels and we produce the image we have here on the right. So we have, and you can imagine all of this actually being pixels on screen, okay? So this image you see here would all be part of a whole set of pixels here. So that looks really terrible, but you kind of get what I mean, right? Okay, so let's try another diagram just to go a little bit more into detail. So let's pretend I have my awesome 3D cube. I have my 8 vertices that fill the corners. And let's look at this one triangle at a time. So in terms of vertex processing, I would pass in these 3 vertices. Well, I'm going to pass all vertices to the vertex shader, but we're going to deal with, because we're rendering triangles, we're going to deal with them three vertices at a time, okay, to make up the corners of the triangle. So this would be our vertex shader or vertex processing, which happens in the vertex shader. Okay, we'll take those 3 corner vertices and then form some kind of triangle out of that. All right, again we have to project how is the camera viewing this cube. Is it in the corner, top down, bottom, looking from the bottom up? What projection do we have, 3D or 2D, those kind of things. Okay, so the vertex processing stage, the vertex shader will determine that. Then we pass on rasterization. This triangle now becomes a triangle made of fragments. Okay, so we can go ahead and we can color these in. Let's pick a nice green color based on, let's say, is the cube textured, is there some kind of light somewhere. So all these calculations will determine what the color of these pixels are. So I'm going to just pretend this is some kind of shade of green. Okay, if this whole triangle was green, yeah, then I'd color these all in like that. So from this stage to this stage is vertex processing. From this stage to this stage is our rasterization. Okay, then from this stage to then the fragment processing would be taking these fragments, coloring them in, doing all the calculations, and then we do the frame buffer operations. That's the final stage where you see that that triangle then drawn on the screen. Of course, then all the other triangles will be passed in as well, so you see that final cube on your 2D monitor in the end of the day. Okay, so what are shaders exactly? Shaders are simple plain text source files filled with code that are compiled and executed on the GPU at runtime. They are programs that essentially shade an object on screen using various color and lighting calculations. They're written and created in OpenGL using its shader language called GLSL, which allows programmers to write various types of shaders. Before we delve into the various types of shaders, let's take a look at various ways of shading. Okay, so flat shading is a type of shading that only uses one single color for a particular polygon face. Okay, and colors and lighting are calculated in the same method for the entire surface. Again, if you imagine this, hence why we deal with triangles in the first place, is because that three points form a polygon that has an equal flat surface. Okay, as soon as you add a fourth vertex, fourth, fifth, sixth, you start bending that shape. So with triangles, they're flat, flat, flat. So with flat shading means this surface here will have the same color throughout. So if it were green, then we can just shade the green. Okay. If you had another triangle with another color, so you can actually see the polygonal shapes. Okay. Just try and imagine the old first 3D games that you saw back in the mid-late 90s that looked very polygonal and every face had its own color. That's pretty much flat shading. So Gouraud shading calculates lighting and coloring at each and every vertex of the polygon and then interpolates the results in between. Okay, and this is usually done in the vertex shader. So let's use our trusty triangle again. Let's draw a nice little triangle here. Okay, and we will get to lighting a bit later on. But basically, we'll calculate what the color is for this vertex and then calculate here and then calculate here, and then we interpolate the colors. So the lighting doesn't look all that fantastic, okay, because it's done per vertex, but it is a lot cheaper than doing it for every fragment. But yeah, the results aren't that great, but that's basically Gouraud shading. So Phong shading calculates the lighting coloring at each and every fragment or pixel of the rasterized image, and this is usually done in the fragment shader. So again, here's our triangle. Okay, if you imagine every fragment that makes up this triangle, and the lighting calculation is per pixel, so per fragment, so more detailed, but because there's a lot more calculations happening than just 3 vertices, it's a lot more expensive. So it looks good, but it's a bit more costly. We will go more into detail about this shading when we get to the lighting video, so just hang tight for that. I'm not going to go into too much detail about this just yet, but just wanted to give you guys a general idea about the different kinds of shading. Alright, so the main language we're going to be using to write our shader code is GLSL, and this stands for OpenGL Shading Language, and is based on the syntax of C. It is a high-level language that allows programs to be written that are compiled by the driver and run on the GPU. GLSL was originally developed by the ARB and introduced into the OpenGL core back in 2004. Coding shaders in GLSL can be done with any text editor or within Visual Studio, and that plugin that we installed earlier is going to help us with syntax highlighting and some minor form of IntelliSense, which is very, very helpful. Alright, so back in my project where all my source code is, I am going to create a folder first of all called shaders. I'm a very big fan of organizing stuff and not putting everything in one place, so let's keep things simple from the get-go. So shaders is going to hold all our shader source code. What we're going to do is create 2 shader files, and literally they're just text files. So I'm going to call mine main, and I'm going to give it an extension of .vert. I'm going to remove the .txt. It's going to complain. It's going to say yes, that's fine. If you cannot see the extensions, make sure on Windows on View you have file name extensions ticked so you can actually see them. Otherwise you may have a function called .vert.txt, and then when loading it there's going to be some issues with that. Second of all, in fact, I'll just make a copy of this. Control C, Control V, and then I'm just going to call it main.frag or FARG. Now, this don't have to call it this. This is just a convention. But generally, .vert.frag mean vertex or fragment shaders. There are different ways you can, the different extension names you can give it, but these are the ones I'm going to work with. So I'm going to say, yeah, that's fine. All right, cool. Back in our program, I'm going to create a filter here. So on my project, I'm just going to right click, say add new filter. I'm just going to call it shaders because I want to be able to see my shaders in Visual Studio and edit them here. And I'm just going to right click add existing item because they already exist. Go into my shaders, grab those and open them up. They're empty now, nothing in them, but they're part of my project. Okay, so starting with Vert, first thing I'm going to do is do a preprocessor called version, and I'm just going to do 400. Okay, now you can, first of all, preprocessor flags, just like in C++, allow things to be set up before compilation. Version just specifies what's the minimum version of OpenGL/GLSL that I want to use. I'm going to use 4.0, which is 400 in GLSL talk. Now you can look this up. If you look at the OpenGL documentation, what the version numbers are pertaining to the OpenGL version. So if it's 4.6 you're targeting, it would be 460, 4.5, 450. But earlier versions have a really weird naming convention. They don't quite sync up, hence why documentation might be more helpful. Anyway, I'm going to stick with, in fact, I'm going to stick with 460 because I know my graphics card can run that, so I'm going to do that. Right, next what I'm going to do is create my main, which returns nothing, so it's void main and doesn't take anything in. Open, close curly braces, and I'll just put a nice little to-do in here and just pretend that something's in here, but it's not. And you'll notice that the code highlights nicely, so this goes blue, this goes white, comments go green, preprocessor flags go gray. Now if you didn't have that plugin, the syntax highlighter plugin that I showed you a few videos ago, this will all just be white, really difficult to look through, hard on the eyes and difficult to debug. But with this you have syntax highlighting, makes your life a lot easier, and you also have some form of IntelliSense. Okay, cool. So my vertex shader does not much, but it's something. And I'm just going to put that straight in the fragment shader as well. Okay, so both vert and frag should have a main. Okay, so at least that's set up. Right, let's just quickly build and compile. Now remember, when building my Visual Studio project, I'm not compiling the shaders. These are compiled when I run them. So when I run the app, click play, now the shaders will be compiled. Theoretically speaking, we haven't actually done any kind of, we haven't written our own compiler yet, which we are going to do. So nothing is compiling just yet, but in theory, the compilation of the shaders happens at runtime. Okay, cool. We have a basic understanding of the programmable pipeline, and we have even created our very first shader files, which do absolutely nothing right now. However, never fear, they will contain some really great GLSL code before long. But first, we need to build the shader pipeline. Quite the task lies ahead, so put on your civil engineering, software engineering hats, and let's get stuck in. Right, before I leave you, however, for this video, here is a complete online guide to GLSL. So if you just head over to this website, shaderific.com, you'll find all the different data types, qualifiers, built-in variables, statements that you can read through in your own time to get familiar with what GLSL actually provides you. See you in the next video.